Eleanor, you have your hand up. Are you just saying hi?
Oh, no, I have a question.
Okay.
So, I was reviewing or like studying our notes for Module 6, and then I have two questions. So the first one is F is never negative because it's actually a ratio of variance, right? And
Correct.
then since the variance in this case are square, and everything will be positive. That's why
Yeah.
it's never. Is that right?
Yes, that is correct. One thing that you might not know is that the F, so when you only have two groups, right? When you do a two-group t-test, which we've already looked at,
Mm-hmm.
if you square the t value, that's the F value for two groups.
Oh,
Yeah, so it's
okay.
t-test, right? Because you can be looking at positive or negative differences between two groups.
Yes.
Is is dual-sided.
Uh-huh.
Looks sort of like the normal distribution. A little bit
Uh-huh.
flatter, but looks like the normal distribution. And so if you square that, everything comes over to one side of the
Okay.
distribution. So yes, it is a positive value, but also for the reason you said, it's a ratio of squared variances.
Why is it called F statistic?
Because we're not original.
Oh, okay.
Um,
Also, I read online that says that when F is 0, it means all means are identical. But I don't understand how can it be 0 if it's a ratio. If it's like 1 to 1, that's 1. That's not 0.
yeah, it's a theory. You can prove it theoretically, but you don't need to worry about that.
Okay.
If everything came from the same distribution, right? If every mean was exactly identical, there'd be no variance,
Mm-hmm.
right? And so
Okay.
that
Okay.
centers you out, and then there'd be no difference. So obviously, you can't have a ratio of 0 to 0.
Yeah.
That's a sort of very odd thing. But if you want to figure that out for real, you can take the biostat theory class.
Okay.
Trust me, no one wants to take that. I took it twice.
Okay.
Yeah,
And
biostat theory is not a fun situation, but if it helps you sort of visualize it, right? If all the means were identical, then the difference between any of the means is 0. And in fact, the
yes.
difference between all of the means is 0. And that gets you over to
Yes.
that left axis.
Okay. And I noticed that there's a note on the end of the module says that if you want to use the post hoc test, you want to use Turkish HSD and not Bonferroni. And
Yeah.
what does that even mean?
Okay. So I'm glad you asked, actually, because I was going to show that. All right, let me share
Okay.
my screen. And I'll post a little video up. I sort of wait for people to ask for it. It's not something that it's on the list of things to cover for this class because we have so little time and so much to learn.
Mm-hmm.
Hi, Ron. I saw
Hey,
that
how you
joined as
doing?
well. So the question here is, the very first question within ANOVA, let me close my video down here. The very first question within ANOVA is, are A and B different, right? Like that's a t-test. Then we get into A, B, and C. And we think about, well, if the F-test says they're different, then where's the difference,
Mm-hmm.
right? So we know I'm reviewing a grant here. Let me get a new document up. Put Brooks's down. Okay, so we know with an ANOVA that we have a null hypothesis of, and I'm just going to call them A, B, and C, right?
Mm-hmm.
All means are, we'll just say similar. Oh, there's my mother on the phone. She's a phone yeller. She doesn't think she is. We try to tell her, but she's like, you yell on the phone too. I'm like, I don't think so. Okay, so that's our null hypothesis,
Mm-hmm.
right? And then our alternative is that there's at least one set of means that are different.
Yes.
Right? So remember, it's not that they're all equal or they're all not equal.
Mm-hmm.
For the ANOVA, we have these following options. We could have A not equal to B, A not equal to C, we could have B not equal to C, or we could have, A not equal to B not equal to C, right? So we could have any number, there's 4 possibilities for the alternative that if we say that there's a difference, it could just be that like A is different from B and C.
Mm-hmm.
It could be that B is different from A and C. And it could be that, you know, B and C are not the same and A is either with B or C. So there's could be 2 means that we're looking for, or it could be that we actually have 3 means. It could be that the mean of A is different from the mean of B is different from the mean of C. And the post hoc test is what answers that. So our first step here is to use the F-test and determine if there is a difference. And is there a difference that's large enough to say that we need to use multiple means? So if you want to think about like, why is this an important question? Think about if you have 3 different doses of, say, Tylenol, right, of a pain reliever. So you can give somebody 250 milligrams, you can go with 500 milligrams, or you could go with 1,000 if they're like in a lot of pain. Not that you'd ever take 1,000 milligrams Tylenol, but you get what I'm saying, right? So you could have 250, 500, and 1,000. And you want to know if this is effective on an outcome. Well, if they're only slightly different, then we don't really want to risk the side effects that could come with higher doses, right? So we need to know, is there really enough of a difference in those doses to say that we're looking at at least two different outcomes? And that's what the major F test asks. This is called our omnibus test, right? Or also called the global test. I can type today. Also called the whole model test.
It's called the omnibus test because it's a whole analysis. Is that why?
It's looking overall,
okay.
Right? So if you think about somebody like the position in politics that's an I can never say it. Omnibus, but yeah, they serve everybody. Like it's the overall test. So it's an omnibus test, global test, or whole model test. You'll also see it listed as the ANOVA test, right? And then we actually use our F test, right? But our decision between our null and alternative hypothesis is the same decision that we've had before. We're going to pick this if the p-value is large. And we're going to pick this one if the p-value is small. And remember, that's less than alpha, right? So it's the same route to our decision. If we pick HA, then we want to know where is the difference. And you guys are not going to be tested on this. You don't have to do this for your data briefs, but you should be aware that there's a couple of options. And this is where we do post hoc test, which means an after test, right? To find the differences. Okay, so there's a couple of tests that you'll hear. One is Bonferroni, and the other that we're going to talk about is the Tukey's, not Turkey, Tukey's HSD is the Tukey's HSD, and there's a couple of other specific tests. Bonferroni is something that people who took stats a long time ago will be like, oh, just do a Bonferroni. And all that Bonferroni does is, okay, let's say I have 3 groups, right? I have A, B, and C, and my alpha level, but there's 3 tests, right? I can do A versus B, A versus C, and B versus C. There's 3 tests to compare. Bonferroni would just divide alpha by 0.05. So let's pull up a calculator, 0.05 divided by 3. And it would say, okay, I now have to compare my A versus B to an alpha level of 0.017. Candace, I see you looking really, really closely. You don't need to look that closely because you're not going to have to remember this. Right? So it's alpha, you just divide the alpha, your new alpha is alpha divided by the number of tests. So here's the problem with that. Bonferroni assumes that all the groups are independent of one another. Bonferroni makes the assumption that I have 3 separate means, but I don't know if, I mean, my null hypothesis up here tells me that my assumption is that I have them, they're all the same. So they're obviously not fully independent of one another. Like it just, Bonferroni is really strict or very conservative in terms of testing. And since go ahead.
What is one example where all means are independent of each other?
Well, that would just be 3 different sets of data.
Okay, I see.
Right? So that would be like, oh, I've got this clinical trial over here, and I have this observational study over here, and I have this group over here. It would be reasonable to assume, since they're from 3 separate populations, that you have 3 separate means.
Okay.
We've drawn from a single population here, and we're looking at an X variable against an outcome. And we want to know if that X variable has different mean levels of the outcome. Our primary assumption up here with H naught is that they're all from a single mean. That means they're not independent. That's our primary assumption, that they all have a single mean. We've decided that maybe there's at least 2 that are different. When we do the post hoc test, Bonferroni starts by assuming they're all different. And that's antithetical to what we've concluded, like where we are right now. So the one thing you just need to know about Bonferroni, so when you go out and amongst your research and you're dealing with people who took biostats 20 years ago, they're going to say, oh, just do Bonferroni. You'll now be knowledgeable enough to say, no, that's the best test we want to do, particularly when you're dealing with small sample sizes. Bonferroni is way too conservative. You should leverage the relationship that your data has coming from the same population. And that basically is the Tukey's test. And so Tukey's is a little bit different from Bonferroni in that it essentially looks at the smallest mean that you have and the biggest mean that you have, right? So let's say B is in the middle. It's going to compare A and C. And if A and C don't end up being different, Tukey's is going to go, you know what, we're done. Like we don't need to go any further. So it doesn't look at all the tests first. It looks at the biggest difference. And if it can declare that biggest difference statistically significant, it'll then look at the rest of them. So one of the reasons we don't go into the post hoc test, and I'm gonna show you how to do this in JMP real quick, is because there's a lot of issues that can come up with it. One, people like to say, oh, well, I found for the null hypothesis up here, and you should stop. If you don't say there's a difference, you're done looking. But people all the time will want to do what we call phishing before email phishing was a thing. They want to fish for significant p-values. They want to fish for something that's significantly different, and they'll start digging into post hoc tests. And that's not really statistically appropriate. Digging into post hoc tests can give you some evidence to plan another study. But if there's no difference, there's no difference. Don't go looking for it somewhere else. So that's one of the issues. The second one is that it can be a little bit tricky. There's a couple of things that can happen with the post hoc tests. You can say here that there is a difference, right? I can find for the alternative. And then when I go do my post hoc test, it's telling me I haven't found anything different. So how can that be? Well, the thing is that once you go into post hoc tests, you're breaking things into smaller sample size groups. So you may not have enough power to declare a difference. Plus, you're adjusting for what we call multiple comparisons. Each alpha that we have, this 0.05, remember that's the likelihood that we make a mistake, right? That's the likelihood that we choose the alternative when the null is really true. That's good for one test. That making that mistake is good for one test. Well, down here, we're doing 3 tests. So the chance that we would make a mistake at an alpha 0.05 actually now becomes an alpha of 0.14. So there's a 15% chance that any one of those comparisons is going to show a difference when there isn't. This is a lot of words. But what Tukey's will do for you, and what Bonferroni did too stringently, is adjust your alpha level so that you're not making a mistake. And that's why we don't really cover this in this class, because it takes a while to sort of absorb all of those things. what you should know is that if you need to do a post hoc test, use a Tukey's. There's a couple of other options. Don't do a Bonferroni, and then find a statistician that can help you.
So does that mean that if you find statistically significant in the first step and then you go into post hoc and then now all of a sudden you don't have any differences, do you still reject your null hypothesis, or
Yep.
do you?
Nope,
Okay.
you still reject the null and say, we've indicated that there is a difference. Once adjusted for, I've typed this phrase so many times, once adjusted for multiple testing, we're unable to determine which groups are statistically significantly different, and you just report the individual values. It's likely a power problem. It's likely that I've got, say, 30 in my omnibus test, but when I get down to it, maybe group A only has 5 people. That's not enough power, right? We talked about what power is. It's not enough power to make that comparison. There's just not enough evidence. So once you get into the post hoc test, you're divvying up your sample size amongst the groups, and you may not be able to declare a significant difference once you've made that alpha adjustment. Because think about like the Bonferroni, which is the most conservative, you'd have to find p-values that are less than 0.017. And that's hard to do. And you need a bigger sample size for that. So let's just hop into JMP so you can see where to get it if you want to play around. But again, if you go to a major research institution to work, there's going to be a group on your campus that's like our Biostat group or the Cancer Center or the CCTS. We can help you. The grant that I'm reviewing right now comes through the CCTS group. So there's going to be a group at your location. If it's a private company, if it's biotech, you'll have biostatisticians. People will be able to help you with this. Post hoc tests are not something you should sort of wade into unless you get real comfortable with it. But let me show you how to do it. So this is the test data that was posted a couple modules ago, and I've just recoded this age group. I'll show you. So the age group in the test data that was posted a couple modules ago had largely 18 to 20-year-olds, and then only 2 26 plus. So I've recoded it now into 3. So I've got 18 to 19-year-olds, 20 and 21, and then 22 plus. So our majority of our students are 20 to 20, or more, majority of our patients here are 20 to 21, but we've got 2 smaller groups. And I would do an analyze fit Y by X on systolic blood pressure as my outcome, and this age group 3 as my predictor. And now we've got an ANOVA here, and I can do my quantiles, and I can get my means and standard deviations, and I can say, okay, so it kind of looks like my highest blood pressure systolic is in my younger students, which seems weird. But it's not that much higher. Maybe they ran to class that day, or who knows. With a mean systolic of 115 in the 21, and then slightly lower in the 22 plus. Maybe they work out more, I don't know. And my question is, my null hypothesis is do we have one mean systolic blood pressure? If I was to look at this age group, if somebody was to be 18 to 22 years old, and they would say, what's my systolic blood pressure? My best guess is this 114.6. That's my overall mean. My null hypothesis is that age group doesn't matter when predicting blood pressure. That I've got that, if I look at it by age, they're all going to have a similar mean BP. When I do my fit Y by X, my gray bar here, right? This is my overall mean at 114.6. Here are my individual groups. Got one big old outlier up here. Ooh, it's 156. And now I want to know, is there a difference? So I can run my F-test, just ask for my ANOVA. And my null hypothesis is there's no difference. And I would stick with that in this instance. I would say, nope, there's not enough evidence that this 118, this 115, and this 106 are different enough to declare there's a statistical difference. So in this case, if this was your real data, you'd stop. This is not a significant p-value. There's no evidence that we have different systolic blood pressure by group. But let's say it was. Let's say this was smaller, right? And we want to do a post hoc test. So in JMP, under this red dot, there's a compare means option. And right here is the Tukey's. So you see Bonferroni's not even on here. Don't do it. So here's Tukey's. The each pair of students t-test is just going to do an unadjusted t-test. So it's going to make no mind of alpha. So you don't want to do an each pair students. You want to do an all pairs Tukey's. This best and Dunnett's, those are for specific. This is if you have a control group. And then this is testing it compared to the highest or lowest. And then there's this other newer test, which you can ignore. So you want to do Tukey's. And here's what Tukey's is going to do. You can ignore the circles. Tukey's, let me bring this up here. Oh, come on. Tukey's has a couple of things that you can pay attention to. So you can see here, it's going to hold alpha at 0.05, and what it does is it adjusts part of the distribution that we look at. If you go back to that T distribution, Tukey's gives you this weird connected letters report. If they have the same letter, they're the same group. But what you really want to pay attention to in Tukey's is this ordered difference report. And so it's going to tell you if I compare 18 to 19 to 22 plus, here's the difference in means. Here's my confidence bound about that difference. And then here's my p-value. So we're not surprised here to see that none of these are significantly different at a 0.05 level because we already knew they weren't different, right? We already knew they weren't different. But this is what Tukey's does, is it then does the comparisons and it makes the correct adjustment so you can report these p-values. So it gives you each of the individual results. But that's a post hoc test. And again, for this class, we can't, I would normally in the next slide, in the 611, 612 classes, we spend about 2 weeks on post hoc tests. And we don't have the time to shove it into a day here for this class. So 2 things you need to remember. Don't do Bonferroni's. And you need to make sure you make a multiple testing adjustment of some sort. And Tukey's is my recommendation. And HSD stands for honestly significant difference, if you were wondering what the HSD stands for.
Thank you.
Sure. Other questions? I'll put your hand down. Anybody else have questions today?
I do. This is Samantha. Going back to Module 5, I printed out the which hypothesis do you use sheet, and I just had a question regarding the divide the p-value in half. I know we divide the alpha in half, right, when it's two-sided?
Well, yeah, so there's 2 ways. If you want a one-sided test versus a two-sided test, depending upon, here, let me pull up a t-test. This will be easier to show. All right, so let's look at fit y by x for gender by systolic blood pressure here. I get my t window and I ask it for a t-test. So the thing is that JUMP gives you all 3. But what do you notice here about these 2? What's the top one? What's this p-value testing? What's this p-value for?
Sorry, I was trying to get my mute. So that one's looking at, that would be for our null hypothesis, right?
Which null though? There's 3, remember? So you could have equal to.
Oh, sorry, that's the two-sided.
That's the two-sided, right? What do you notice about this p-value right here in comparison to the?
Oh, it's like half. It's smaller.
It's half, right? So this is the one-sided greater than. It's half, right? And so JUMP already does it for you, right? So you can either, the two-sided test puts 0.05 alpha on each side of this distribution, but the one-sided test puts it all over on one side. Mm-hmm. So you can leave your alpha at 0.05 and look at these And this is actually your alternative.
Mm-hmm.
So whatever your null hypothesis is, if your null hypothesis is equal to, then your alternative is not equal to, which is represented by the greater than absolute difference. That's your null. If your null hypothesis is less than or equal to, I don't know if you guys noticed, but if you leave your mouse sort of hovering over, Jump will give you some little info. But if your null hypothesis is less than or equal to, then this is your alternative hypothesis, greater than, and you can report this p-value. And if your null hypothesis was greater than or equal to, then this is your alternative of less than, and you can report that p-value. And so when you look at this sheet right here, these out of the way, right? So here's my null hypothesis over here on the right, this one, of equal to, and here's my alternative of not equal to. That means I'm reporting this p-value. Right? It means I'm reporting this p-value. If my null is this one right here, greater than or equal to, then my alternative is less than. My alternative is less than. That means I'm reporting this p-value. Reporting this p-value. And if I'm greater than or equal to as my alternative, then I'm reporting this p-value right here. Okay? But keep in mind, you would never test, like I've got a 117 and a 113 here. Like I would never test that 113 is greater than 117. That doesn't make any sense, right? So you do have to have some kind of knowledge. If you don't know, oh geez, this is one of the quiz questions. If you don't know, then use the equal to, not equal to. Do a two-sided. If you have no preference or you have no understanding, if this is the first time you've ever compared these groups, then it's equal to, not equal to. I'm working on a grant right now where we are only interested in if this diet, these people lose more weight than the other group. So we're going to do a one-sided test. We're only going to look to see if it's better than. Because I don't care if it's less than, right? I don't care. If the new diet loses less weight than the standard diet, then I don't care. It's not helpful. I only care if it's better than. So we're going to do a one-sided test in that grant. And this is, again, where I say to you, you guys are learning a lot in this class, but you sort of leave this class with some training wheels on still, if you use a bicycle analogy. Like, we're going to teach you how to ride the bike, but you're leaving this class with some training wheels. So if you get out of here and want to design your own study, get some help. Because the statistician can help you sort of think through those problems. But yeah, so that's how these line up with this. Does that answer your question?
Yeah, it does. And with that, I didn't get a chance to look at your video for the Learning Check 5, but so if you answered it, then let me know. But in the video, I think by Dr. Austin, she was saying the importance of making sure like Jump will automatically put the second group as the first group. And I think in the Learning Check, I had accidentally put it as a negative value when it was supposed to be a positive value. And I was feeling so confused as to what I did wrong because I had recoded male. It was with male and female. So I don't know if you could talk about that at all.
Sure. So you can see here that it did. So all stat programs, by the way, bring variables in alphabetical order, which is why value ordering is so important. So it's going to bring this in female to male, right? This F comes before the male. So therefore male is going to be, it's weird. Then it reverses it and does primary category. So you can see, and the way that you can tell is here are my means, 117.8, 113.3. My difference here is 14.6. So that means it was 117.8 minus 113.26.
Okay.
Right? So it's giving me a positive difference. That means it's looking at males, female. The two-sided question doesn't matter, right?
Right.
This right here, this middle one, is a p-value for whether or not this difference is greater than 0. And that means it's testing are males greater than female. Let me walk you through this real quick. To another page here. So our null hypothesis here, right, is males equal female. My alternative, males not equal to females. This is for the two-sided test. This then becomes males minus females, and this is their means, right? Do this. So the null hypothesis that the t-test actually looks at is this, right? And I got 117.85 minus 113.26, and it's going to give me a 4.59 here. So I want to know is 4.59 significantly different from 0, right? That's really my question. Is the difference I see between them different from 0? So over here in JUMP, this two-sided right here is for this alternative. It's for this alternative. And that's my prob greater than absolute t, right? If I happen to have an alternative of males greater than females, that's my prob greater than t. And if my alternative is males less than females, that would be my prob less than t. And it should be fairly obvious why this p-value is so large. Because males are 117 and females are 113. So I'm never going to say that 117 is less than 113. So you just have to think about what your question is in advance. I don't know if that answered what you were.
I think it did. I'm going to go back and look again. And but I think that does make sense. Thank you. I was just feeling like, oh no, if it takes the second group and puts it first, like I was feeling very confused.
You can always tell by looking at the difference. What is this difference? This is a positive 4.58. That means they did males minus females.
Okay, that makes sense. Thank you.
Let me just do for show of cause here. I'm going to show you something real fun. I know my definitions of fun is different than yours. I'm fully aware of the things that I think are fun are different than what other people think is fun. So I've switched the order. So you can see here just by the graph alone, female left, here is male left. I've switched the order. And if I ask for my pooled t-test, my difference here is 4.58. My difference here is minus 4.58. My t-ratio here is a positive 1.3. My t-ratio here is a minus 1.3. My two-sided p-value, guess what? Exactly the same. And then the only thing that's changed is the p-values here have flipped because I've changed the order of my subtraction. You see that?
Yeah, thank you.
Yep. And then you'll notice that your ANOVA table here hasn't changed at all. Because ANOVA just asks for difference, no difference. And if you're real fancy, like I can be real fancy in statistics, my t-value here, right, 1.30153, 1.30153 times 1.313 is a 1.6939. Look at that. Square a t and it's your F when you only have two groups. That's why it's a two-sided test. It takes this part and puts it over here, puts it over on that side. Just makes it all positive. So when you have two groups, square your t value, you'll get your f value. And that goes back to the first question that we had about f is always positive. Neat things about distributions.
Thank you.
Sure. Other questions?
I have a couple questions.
Mhm.
The team assignment that's due on Monday,
Mhm.
the 22nd.
Yep.
You've asked for three things. Hypothesis, that's self-explanatory. I don't, and I may be showing my ignorance, but I don't know what a data dictionary is. I'm sorry.
Upcoming team assignment announcement.
Okay,
Okay. So I made an announcement about this last night.
right,
Provide an expanded data dictionary. So you guys have been looking at them as code books,
right,
right? The code book takes the raw data, how it was entered, into analyzable data.
okay,
Your data dictionary does the same thing, just takes it one step further. So let's say in your code book, you've got, it takes the 1 through 7 on race
yes,
and gets you the named categories.
right,
Your data dictionary is going to tell me how you analyze that data. You might not use all 7 race categories, right? So you might look at white, black, other, or you might look at white, black, Asian, Hispanic, other. You might look at single race versus multi-race. So the code book takes it from how the data was captured
right,
to the right categories. Your data dictionary is going to tell me how you analyze it. So how's that data different? And in a lot of cases, it won't be. It's just going to be your, let's Google here. Data dictionary. Google's your best friend for everything in life.
right. But data dictionary was not something we've discussed at all. Is that correct?
Correct. Sometimes I want you to look things up.
That's what I wondered.
Yep. So here's an example of a data dictionary that looks a little bit similar to some of the code books we've seen. This actually just has like first name, last name. It tells you what data type it is. This is a real specific one. For you all, we can think about one that has, let me see if there's one that has listings as an example here. These are all like weird data dictionaries. Student details. Yeah, these all have a lot more information than you. Here we go. All right. So this is what we've seen from sort of our code book, right? Here's like the category name. Here's the information. And we could see that we had like a 1, a 2, a 3 in our code book.
Right.
And then what's like, oh, hello. I love it when we have kids join stat classes. Like get it into your brain early, right? And so then you can see here, like what's the language that's in this information. So it provides it, oh, I didn't mean to click on that, but it provides like another level of how you're going to use it.
Okay.
So it's just simply a listing of your variables. What are the categories? And then are you doing anything to it for your analysis? So, because most of you have picked, like, let's say you pick NHANES and it's got 1,000 variables, but you're only going to be using 4 or 5 of them. So I want you to create your data dictionary for your data brief.
Okay.
And then the preliminary summary table, you guys did a preliminary summary in Learning Check 3. We provided you the table template, the bottom of Learning Check 3. And you've, seen some examples in your lives as well. We often call this table 1. So if we go to, let me take a look at my Acrobat. Let me open up a recent paper that I was looking at here. Doo-da, doo-da. My computer wants to cooperate. It's been real mad this week. Let's see if it's here. God, I can't type today. I have it here. All right, here's a good one. I'll look at this paper. So this is a published paper, and when you start to see published papers, you'll start to see very commonly something called a table 1. This is a real common thing, and it is your cohort description.
Okay.
Now this table 1 has kind of collapsed a couple of things in it, but you can see that our variables of interest that we've looked at here are gender and then type of MS. And then we've looked at them across relapse history, time since most recent relapse, and duration. How long did their relapse last? Let me pull up another one. Let's go into, let's go to my downloads and have me pull up another paper here.
So table 1 in each of our data briefs that we look at is usually the summary of the cohort?
Yep, cohort summary, access and utilization. Let me pull up, I'm seeing if I can find another one. So here's a different one in premature infants. This is a clinical trial, and you can see here they've got the table 1, the maternal and neonatal demographics by treatment group.
Okay.
It's just a little bit bigger. And so they've got the maternal age, gestational age, the gestational age stratified, infant sex, infant race, cesarean delivery, maternal diabetes. So these are all their demographics, and then they've actually split it up by their 2 treatment groups. This is a clinical trial. You could actually do your summary overall. You could do it by gender. You could do it by age. Just depends on what's important to your data brief. All I'm looking for right now is just a summary of your demographics that you're using. Most of you have used age and race that I've looked at. I'm in the process of grading that first one. But so far, so good. They look good. And then you'll want to report a sort of general proportion of your outcomes. So if we're looking at health insurance, right? 87% of the people in this have health insurance. We're not doing any fit Y by X yet. That's the next assignment. This is just a summary of the variables that you've provided in your dictionary in a table 1 scenario.
Okay, thank you.
Mm-hmm.
That helps a lot.
Sure.
So just to sorry.
We're meeting tonight, so that's why I'm trying to
Okay.
determine what exactly our goal is, because I really couldn't, but anyway, that helps a lot. Thank you.
Yeah, and so remember, these team assignments are also drafts.
Right.
These are to help you guys move along throughout the course of the semester so that you can have the pieces ready, and then you can also amend them. So I'm going to read them and make some comments back, and so that you can sort of get better each time. Just make an honest effort at it. Okay, next, somebody else had a question.
I feel like I lost it. It was based on, I wanted to clarify what you had just said. So it's not fit Y by X, just a summary of the variables, but I lost the.
That's okay. If you think of it, just shoot me a little Canvas mail.
I did have a quick question though regarding the data dictionary. So I did quite a bit of research also on Google, and I found I just wanted to clarify the categories that we would be needed, because so I have variable name, description, the type, and then the values or the characteristics. Would that be sufficient?
Yep. Make sure you give the levels, right? So some people, so the National Surveillance Data Systems, here's a good example, does income level in a really weird way. I don't know if anybody's run across that yet. They look at it as a percentage above poverty. So that needs explanation in your data dictionary. So things like male and female are pretty obvious, right? If there is a yes-no variable, what does the yes mean? What does the no mean? Because you got to look at the questions. Some of the questions can be weird. My favorite questions are double negative questions where the yes actually means no, or the no actually means yes. Have you not had? No, I have not had. Well, that means you've had, like it's so make sure you understand what the levels of your variables mean. I've had people in prior years do a mean race, right? So make sure that you've recoded your data so that you can report ends and proportions. I'm trying to think of other common pitfalls. Yeah, that's about it. Make sure you list the questions, you know, with the data that you have, especially for the outcome ones. What is the question that goes with it?
And then I just remembered my question again. Thank you. When we're not doing fit y by x, just a summary of the variable for the whole population. So we're using the drug survey, and it has a ton. I mean, we're only looking at youth a certain age. So would we data filter just the ages that we're looking at?
Yeah, that's a great question. So this is an excellent opportunity for your team to create the subset that you're going to use for analysis. All right, so you guys, you're in one of the first 4 teams, I think. Right.
I'm team 13.
Okay, somebody else is using the 8 oh no, that's the tobacco. Somebody's doing youth tobacco. An age group comes in 12 to 25, I think. So they actually restrict their ages. So instead of doing a data filter, if you're only going to be looking at people that are 18 and younger, create yourself a subset of data to work with so that you're not constantly having to data filter. So for example, let me go into I meant to do jump here, into my test data. So let's say this was your data, right? And you only wanted to use people that were young, that were 20 or younger. Rather than having to filter the data every time, I could look at my distribution, and I thankfully have my age groups set up this correct way. And if I just want to look at 20 and younger, that's these 2 groups, right? So here's my people that are older. I've got them selected. I can either delete them or I can invert it, right? Now I've got my 18, 19, and 20-year-olds and do a subset so that the data that I have is now restricted to the people that I'm going to be using. And then just save this for your data brief so that you're not working with that really cumbersome giant data set you pulled down. And also, now's a great time for you to restrict your columns to the columns that you want to use.
Okay, and then with that, would we just save it and then share it so we could all use the same? Yep. Okay, perfect.
Absolutely. That's a good use of either your Microsoft Teams page or your groups page on Canvas. So just post the file so that everybody can have it. And then if you want to know, this is already a small data set, but let's say that I just wanted to restrict it to age and gender. I've got all the rows selected. I can then now just select age and hold the command key and select gender. So now I just have these 2 columns selected. And when I do my subset, there's this option here. Do I want all columns or do I want just the selected columns? And if I click that, press OK, now I have my 18 to 20-year-olds and I have my 2 columns. So that's how you can reduce columns, or you can individually go through and delete them as well. But it's a lot easier if you just restrict it to the data that you'll be using.
Okay, perfect. Thank you.
Yeah. Data filters are great for quick things, but it can make it confusing, especially if you're data filtering on a continuous variable. Getting it at exact right spot on the continuous slider can be hard on the filter. Other questions? I like to eat ice. I know it's bad for my teeth.
Sorry, I have one more question regarding this subject. So with the data dictionary, for example, in my variable that I'm looking at, 999 equals missing data and 7, if we're going to exclude that information, should we also exclude it from our data dictionary?
Your data dictionary is where you want to say a 999 was missing, and then in whatever your next column is you can put that will be excluded for analysis.
Okay, perfect. Thank you.
Will this help session be available for review tonight?
Yeah, it should be later tonight.
Okay. How much later? We've got our conference at 6. I just wondered if I can go back over this.
No, I've got it might be, I've got another call right after this. It just depends on how busy YouTube is.
Okay.
It's got to filter and,
Very
I'll
good.
try. But you took good notes, Ron.
I tried to.
Yeah, so what happens is this records on my computer and then I go in. We started right away, but it shouldn't have too much to edit out. And then I have to render it. And then it has to upload to YouTube and process there. And then I got to post it on Canvas.
Thank you.
Anybody else with any other questions?
All of the Zooms are, I know I saw your video, but I only can see the ones from Christina.
So,
I don't know what I'm doing wrong.
No,
Am I
you're not
supposed to
doing
go to YouTube?
You're not doing anything wrong. So I posted a little announcement about that.
You have to go to Zoom to find them, right?
So Christina's are in Zoom, right? Christina's are in Zoom. Hers are done directly on the cloud.
Mm-hmm.
Mine are not, because I edit out stuff that not everybody needs to see. So mine don't record to Zoom. Mine get posted under modules.
Oh.
And then there's actually a module that is called Live Zoom Live Sessions.
Okay.
Good Lord. So the Zoom Live Sessions, you can see there's much, what is going on here? Canvas is being so persnickety. You can see my Zoom Live Sessions here have the office hours. So today's office hours will go under the June 10th. Here's just how to find Christina's, which are over in Zoom, because I don't expect her to do any editing. These are some of the questions that people have had about JUMP. That sometimes it's easier for me to record a quick video. And then here are the LC reviews.
Okay.
And so that's the thing, is that if you have a question about something, just shoot me an email and I can record a quick little JUMP video and post it here for everybody to see. This is sort of how we deal with the learning by osmosis if you were in a classroom. Other questions?
Thank you very much. I'm going to leave.
Okay.
Yes, thank you very much. I appreciate it.
Absolutely. Hi, sweetheart. How old is she, Candace?
She's 5.
Oh, what's her name?
Kyrie.
Kyrie. Hello, Kyrie. You should be a statistician. No, I'm just
Say hi, Kyrie. No. She's shy. She said no.
kidding. No. You'll always have a job.
Turn it down, though.
That's right.
Okay, you're about to get out? Good.
Okay.
Okay.
She's adorable.
Thank you.
Good for you. I can
Yeah,
barely manage myself.
She's been pretty good, too. Oh, I've been struggling over here, but she's been pretty good.
Yeah. Good for you. Do you have any other questions?
I think I'm good. I think for the most part I have it. I think I'm good.
Okay, fantastic. Have a good
All right.
afternoon.
You too.
Anybody else have questions that's left on?
Okay, so I think I have some questions.
Okay.
So I've been trying to go over the modules from the very beginning. Because especially this being online, like it's hard to absorb everything.
Yes, it is.
So going through from like, I think it was module 2, when looking at the videos for the data preparation and data exploration from Dr. Austin. So when the distribution is skewed,
Yes.
which numbers are best to report? I think it's the 5 number summary but I'm not sure.
Okay, why do you think it's the 5-number summary?
Because of the quantiles.
Yes, that's the short answer. Yes.
Okay.
Yep. So when data, so this might be a little bit more helpful. When you report a mean and standard deviation, you are implying that your data is symmetric. You're implying that it looks like the standard normal, right? That plus or minus 1 standard deviation contains the same amount of information, plus or minus 2 contains the same amount, and plus or minus 3. If your data is skewed, that's not accurate.
Okay, yeah.
Yep. So and by the way, when I say skewness, we're talking about like severe skewness, like a couple of outliers, not really a problem. But if it's, pretty wee, then, and that's my verbal interpretation of skewed, wee, going down a slide. If it's pretty steep with a long tail, then the 5-number summary is the best representation.
Okay. Okay, I have another question.
Sure.
So on your video, when you were doing recoding, so I'm getting a little confused when watching Dr. Austin's video. So when there's, when you change a variable to categorical,
yes,
is it best to change the labels when you, I guess, okay, let me try to word this right so I don't confuse you. For categorical, are you only supposed to use value labels? Are you supposed to change the values through the value labeling?
Okay, so there's 2 options as we've talked about. So if we think about something like gender, right, there's only 2 options, male, female, in most of our data sets. Not true of every data set, but in the data sets we'll see here, we've got male, female for most of them. You can value label them, but remember, until you change it to categorical, it's still going to be a number in the background with value labeling. I am a big proponent of simply recoding everything, leaving the raw data in one column and having a new column for the recoded data. And that way, if you ever have to go back to the original, you don't have to worry about it. It's still there. And then things like, if you look at this age distribution, this is in the NHANES, by the way. There are not people that are 6 and 9 years old in NHANES. These are different codes, which is really confusing because it's a continuous variable.
Is the screen supposed to be up?
It is. I stopped my share. Sorry. Thank you.
No, that's okay.
Push the wrong buttons, right? So in the NHANES data, like there's not supposed to be 6-year-olds in the NHANES data. And so some of these have to be, these are either like the 9s might be missing or else these are just the wrong ages. So you'd have to exclude them. Like, so I feel like it's just better to recode it.
Okay.
And when you get to be a little bit more sophisticated, I use formulas to do most of my recoding rather than using the recode option. So if you look in the test data here that I had, I could easily recode this, but I actually just did a formula instead.
Yeah.
So it just depends on what you're most comfortable with. I think value labels are fine if you're careful. To make sure that you got the data specified correctly. It's just best practice to make a new column.
Okay. That's good. I just needed clarification on that. And also, I know that you were talking about axis settings in that video. To right click it, and for some reason on my computer, anytime I try to right click the distribution, I can't find that setting.
All right, so let's go to the narrow, wide, and the ANOVA, right? This data, new one. So if we do analyze fit y by x, my group is my x, and we'll do the narrow. It's very clean data. Your data will never look like this. So, I mean, it should just be a right click to access settings.
Okay.
So just hover over, and then I'm on a Mac, so it's control click.
Yeah.
Are you on a Mac?
Okay. Yes, I am.
Okay. So that's how you right click on a Mac, is control click. So press the control button and then click your mouse.
Okay.
You can set up, do you use a trackpad or are you on a mouse?
I just have the trackpad that's on the laptop.
Okay. So you can actually in your settings set your trackpad up to have a spot that's right click where when
I didn't know that.
Yeah.
Okay.
So if you want to, go into your settings and you can set up your trackpad to do that, but it's just hold the control key and click and it'll right click for you.
Okay. Perfect.
Yeah, it's a little tricky
And
with two separate operating systems.
yeah. And so as I go through the rest of these videos, we can always just email you and set up a separate time to do a Zoom call, right?
Yep.
Okay.
You can also contact Christina. Her schedule is slightly more flexible than mine.
Okay.
So she might be able, and she's one of our DRPH students, and she's an excellent jump user, and she's super smart. So depending upon what your schedule or my schedule looks like, you can also just reach out to her.
Okay. Sounds good. Thank you.
Absolutely. Other questions? Anybody? Sipu, I see you changed your name.
Hello.
I see you changed your name. Sipu.
Hello. Dr. C, I'm Apurva.
You're Apurva. Okay.
Yeah. Hi. Actually, I had some doubts regarding the team assignment. Can you explain me like what exactly the data dictionary means? Is it like just the variables and the values that we have to copy on Word document? Is it like that?
Yeah, it's in a Word document. So the code book that you have for your data is going to be way too large.
Okay.
Right?
Yeah.
So you guys are restricting your data to probably 5 or 6 variables.
Yes.
And you may not be using the variables in the same way that they are in the code book.
Yeah.
So most of you, if you're using race, there's going to be anywhere from 5 to 9 categories for race. That's going to be too many for analysis, really. And so you might be combining them into white, black, multi, Hispanic. You might be taking it from the 9 categories to 4 categories.
Okay.
Your data dictionary would be where you show that.
Okay. So we have to do the data filter and copy the, like, for example, like I do a data filter in the race and then I copy that into my Word document.
No. So the data dictionary needs to be something that you make. It's not jump screenshots.
Okay.
If you Google data dictionary, which we did on the earlier part of the call.
Oh, okay.
So if we look at, you are making a code book for you.
Okay.
And for your team. And so you'll start to see here that it's got like, what's the data called? What's the data type? How's it formatted? Instead of, this is a very simplistic one because these are all pretty straightforward. But if you had different categories for things, oh, there goes my dog. So if you had different categories for things, that's where you'd list them.
Okay.
So this has got London, this has French and English. You can think of this one. And then they've got a language subcategory. So the data dictionary is going to specify what your variables that you're using will look like for your data brief.
Okay.
It takes it from the code book to the data to how you do it for analysis.
Okay. Okay, so the table form should be in the Word document. We have to make a table in Word.
It doesn't have to be a table. They can be bulleted out. You guys only have maybe six variables.
Mhm.
Another good example is I looked at one group. That's looking at vaccines, and they
Okay.
have 0, 1, 2, and 3 shots.
Mhm.
But then 3 is really small. Like, there's very few people that have had 3 of this vaccine. And so theirs is going to say that here's the variable that we had. Here are the options, 0, 1, 2, 3. For our analysis, we're combining, it's going to be 0 versus any.
Oh, okay.
So they've
I got it.
taken the steps to what they're going to do. I've got
Okay.
another group that is restricting their analysis to people under the age of 18, 18
Mhm.
and younger. But the big data set goes up to 25. So they specify the variable name, that it goes from 18 to 25, that anybody that is 19 or older is going to be excluded, and that they then instead of categories for their age can use age as a number.
Okay. Okay. I got it.
Mhm.
Yeah. And the summary table, this is the same table which you had asked us to fill in the LC3.
Yep.
Like in the same format, we have to fill it.
Yes.
Okay. Okay. All right, Dr. C. Thank you so much.
Absolutely.
Bye-bye.
Any other questions? Okay, if you guys think of anything, I will be on until 5 o'clock. Okay?
Thank you.
Absolutely.
Bye-bye.